Hi guys. Today we're going to continue with our problem solving for linear algebra. So we're still solving problems that are connected to our second lesson of linear algebra, which discusses the algebraic notation of representing matrices. So we are going to look at another interesting problem, which will train you on how to effectively use the algebraic notation of matrices. You see, so this problem that you are going to look at today, it's going to feature what are known as Markov matrices. You see that? So, what are Markov matrices? So the Markov matrices are special matrices that are used mostly by the finance people or statistician. You see that? So what they use them for, this is beyond the scope of this lesson, but you can do some research to gather more information on what they are used for in finance or statistics. But by definition, Markov matrices are some special matrices which are, you have the following characterization. So if you had to add all the entries along a particular row, you always get 1. So every time when you add all the entries along a particular row, you always get 1. And also when you add entries along a particular column, you always get 1. You see, like that. So this is one thing that characterizes these type of matrices that we refer to as the Markov matrices. So a typical example of a Markov matrix is something like this. So if maybe we have 0.9 here, 0.1, then 0, 0, and then maybe 0.1 here, 0.8, 0.1, 0, and then here also with 0, 0.1, 0.8, 0.1, and then 0, 0, 0.1, 0.9. This is an example of what we call a Markov matrix. So if you are to add things along a particular row or a particular column, you will see that you always get 1 out of that. You see. So this is an interesting characteristic because we can see already the connection that this thing has with probability, because we know that every time when we have a certain experiment which has a possible set of outcomes, we know that the probabilities of each of those outcomes, when added together, they give us 1, which is exactly what you are recognizing here. So which can imply that the entries of a Markov matrix might be connected in some way to probabilities. But that's the subject of another day. So today, let's look at exactly what is the problem that we want to solve in connection with this. You see. So the problem that we want to solve in connection with this, it goes as follows. You see that? So Q. Prove that if A and B are Markov matrices for which AB is defined. So prove that if A and B are Markov matrices for which AB is defined, then AB is also a Markov matrix. You see that? So this is an interesting problem because it kind of shows us that being Markov is a preserved characteristic. You see that? It is preserved in the sense that if you have a world full of Markov matrices, every time when you put them into a product, if that product exists, you always get outside a Markov matrix, you see. So now what we're going to do is we are going to actually see how we can go about proving a problem like this one. You see, how can we prove that indeed if two matrices are Markov, their product is also a Markov matrix? You see. So let's get to the solution of this problem. So it will be good to try and think it through and see how we can actually try and approach it. And then after you have tried it out, you can then compare your solution to the solution that is going to be provided in this video. You see. So now, what we're going to do is, as a solution, I will say suppose A and m by n and B, which is an n by p. Suppose A and m by n and B and n by p are Markov matrices. So that's one thing that I will suppose. I'll say, let's assume that these two matrices, A of order m by n and B of order n by p, are Markov matrices. But what does it mean then to say that a matrix is Markov? You see that? So, if A is Markov, what follows? If A and m by n matrix is Markov, then what? Then for all k, so we know that if m by n matrix, this one is Markov, then for all k with k running through all the rows of A, so with k greater or equal to 1 but less than m, we have that sigma of A k j is equals to 1 for all j. You see that? So this is what it means for a matrix to be Markov. You see that? So in this case, the j, they range along the column, so they range from 1 to n. So that's what it means for A to be a Markov matrix. You see that? So if A is a Markov matrix, this has to be the case. So if A is Markov, then for all k, so when I say for all k, it means for all the columns, you see that the sum along the row has to equal 1, like that. So that's what exactly it means. So that's what how we interpret everything that I have written here. And also, if B and n by p matrix is Markov, what does it mean? Then what? So if B is also a Markov matrix, then it means for all L, yeah, it means then for all L, where L ranges from what? With L ranging along 1 to n, we have that. So we have that sigma of B, Lj for all j is equals to 1 with, but I don't want to say j because it will confuse, so I'll say j prime, with j prime ranging from where to where. So B is column ranging from 1 to p, so j will also range from 1 to p. So that's what it means for these two matrices to be Markov. You see that? So if A is Markov, this follows. If B is Markov, this follows. Now we want to prove that the product of these two Markov matrices is also a Markov matrix. So how can we now prove this result? You see that? So to prove this result now, that this is how we're going to proceed. Now, let C be equal to AB. So now we'll assume that the product of these two matrices is another matrix, C. And we know definitely from the order that we have defined, since we say that B was n by P and A was m by n, we know that this thing is going to be m by P matrix. So we'll say let also this be equal to Cij, like that. You see. Now, we know again that by definition, AB is defined as the sigma for all k of A, Ik, B, Kj. So by definition, the product of two matrices A and B is defined as follows. You see that? It is defined as sigma for all k, where k is taking all possible values, and then we write these juxtaposed like that. You see? So now what we want to prove next is we want to prove now that this matrix C, which is created by the product of A and B, is also a Markov matrix. You see that? So now what do we know? So it follows from here that each entry in matrix C is just defined as Cij, which is just simple all k for Aik, B, Kj. So this is the representative of each and every entry that lies in matrix C. So what we're going to do now is we are going to test now that is it the case now that the sum of things along any row, is it actually equal to 0? Is it equal to 1? I mean, that's what we're going to test now. So to do that, we have to fixate ourselves in a particular row. So now, to fixate ourselves in a particular row, what we're going to do now is, remember rows are defined by I, while these columns are defined by J. So what I'm going to do now, we'll say let's fix I at S. Then what? Then now we have C Sj, which is sigma all k. Sorry. So what we're going to do, we're not just going to fix ourselves at Lj. So what we're going to do, remember, we want to prove that the sum of all the entries along a particular row is equal to 1. So which means we will fix ourselves at S, but we will then add everything along that row. You see that? So how do we write that down? So to write that down, we will find the sum of C Sj for all j. So this means I'm fixated at row S, but I'm summing along that row. So I want to find what is the sum that I'm going to get when I'm summing all the entries that lie in row S. So by definition, this is just the same as saying sigma all j of Csj, which is just that because Csj can be created by putting S where there is I in this definition here. You see that? So which means I'll bring that whole thing to get sigma all k of A Sk B Kj. So that's what we get now. Now we are sitting at this point. So how can we proceed from here now? So to proceed from here now, we are going to recognize something. So if you look closely, you will see that this outside sigma notation is summing using j, which means it's independent of the k that is inside. Remember, both k and j, they are changing because they are taking different values as we move. But the outside sigma notation will only affect the term that is that j variable. So which means I can take this sigma and send it directly to sit next to b because it's only affecting only that term. You see that? So since it only affects that term, I will have here sigma all k sitting and waiting, and sk will sit next to it. Then this sigma j will come here, and we have all j, b, k, j, like that. You see that? So now let's just focus on this part and see what's going on here. Let's be observant and see what's going on here. So if you can look at exactly this thing that I have highlighted there in red, you will see that at this instant k is fixed, but j is going. So since k is fixed and j is going, it means this thing, it is summing all the entries that lie in matrix B in row k. So that's what is happening here. So this is the sum. So let me just add this comment. So what we have here is sum of entries in row k. That's what this thing in red is. It is represent the sum of all entries in row k. But if you remember very well, the matrix B itself is Markov. You see that? So since this matrix B itself is Markov, this sigma notation must evaluate to 1 because it's summing things along a row. So since we're summing things along a row, we expect that thing to be 1, which means we'll get this sigma all k ask. You see? So let me add also another comment. So this is equal to 1 since B is a Markov matrix. You see that? So since B is a Markov matrix, that expression in the red box is going to sum to 1 because its summing entries are in row k in matrix B. So that becomes 1. Now let's come now and look at what we have just landed with here. So if you look here now, this object that we have here, it is sum of entries in row S. So this is the sum of entries in row S in matrix A. That's exactly what this object is that we have here. But already A is a Markov matrix. So which means if you fix yourself at S and sum around K, you still have to get 1. So which means this whole thing has to give us 1. So, but now what do we see here? So now we can see that therefore, for all S, we have that. So for any S, yeah, let me write it like that way. So for any S, we have that sigma all j of CSJ is equals to 1. Thus, C equals to AB is also a Markov matrix. You see, so this is a very interesting problem that you have to make sure that you understand everything that was going on here. So try to practice it, to also redo it on your own and understand each and every line that you do, why this follows from that. Because most of the time when questions on proofs are asked, these are the typical questions that are asked. How does this line actually follow from that particular line? So this problem that we solved here is a very interesting one, and it will actually train you how to handle most proof of this standard in linear algebra. Otherwise, thank you for watching, guys. Meet you on our next session together. Thank you. Bye.